Hello, everyone. How's it going? My name's Hollin Wilkins. This is my friend and colleague, Mikhail Semeniuk. For the past year, we've been developing two technologies, one called MLeap, one called Combust ML. Both of them have a common goal, which is to allow you to easily deploy your Spark pipelines, scikit-learn pipelines, even TensorFlow models to a common runtime that you can execute on edge devices or in the cloud and easily manage all of them. So just a brief introduction. For the past 4 years, I've been working on high-performance API servers with Erlang and Scala, and about 2 years ago, Mikhail and I met and started working on machine learning platforms together.
Yep, and I'm Mikhail. Brief intro myself. I spent most of my career as a statistician, data scientist, working in healthcare, automotive, web, and most recently in signal processing and image detection. And before we kind of go into how MLeap and Combust works, we actually just want to start off with a demo. And this is probably one of the few presentations where we're going to encourage you to take out your cell phone and navigate to, essentially it's a web form. Right now, it's not hooked up to anything, but the purpose of this web form is to essentially tell you how much you should be renting your house for, like on Airbnb. And if you can see now, if you go on there, it says model does not exist, can't make a prediction. But what we're going to show you is how to run a Spark pipeline on roughly 400,000 listings that were publicly available from Airbnb. Put together a Spark pipeline, train both a linear regression as well as a random forest, and deploy that literally with one line of code. And just want to stress, and we'll talk about this more, not deploy just the model itself, but deploy all of the transformations that have to happen to the data before it goes into the model. Yeah, if you want to go through them.
Yeah, so this is just a little notebook that we put together. All we do is we load up our Airbnb data set. We do some filtering on it. We do some imputation in order to generate values that aren't there. We sort of explore the data a little bit. So here we're trying to figure out what the most popular cities are on Airbnb. Here we try to figure out what the most expensive cities are on Airbnb. And I'll just go back to these real quick. So most popular city, well, actually, I guess we did it by state here. Most popular in order, New York, California, Paris. Then the most expensive ones tend to be beach cities. So that sort of makes sense. And then here what we're doing is we're defining all of the features for our pipeline. So we're defining our continuous features, we're defining our categorical features, and we're sending those both through their own data transformations. So with continuous features, we actually do standard scaling on it, which is just scaling each of the features based off of their standard deviation. For categorical features, we do string indexing, one-hot encoding. And this code is just putting together the feature pipeline. And then what we do after we have all these features into a feature vector is we actually train a linear regression off of it, and we train a random forest model off of it. So this is all just out-of-the-box vanilla Spark at this point. We've done nothing special. This is just how you would train a machine learning model using MLlib ML pipelines. Where it gets interesting is we've built out this whole platform around these things. So essentially what we can do is we can serialize that entire model that you've just built, that entire pipeline. We serialize it to a format that I'll talk about later, and we can actually upload it to our servers and start serving the models with just a couple lines of code, actually just one line of code. So this is all boilerplate here, getting everything set up, setting up our client to actually talk to 2 model servers that we have running in AWS right now. And then this is the one line of code that I want to talk about, this client.deploy. All we're doing is we're sending in the Spark pipeline for the linear regression that we trained, as well as a name for our model that we want to run in the cloud. And I just ran that, actually. And now we can go over here. And we can see that we're actually immediately getting results back from that pipeline that we just trained in that notebook and literally deployed in maybe 30 seconds. Now, if I switch over to random forest, I still haven't deployed that one. Model doesn't exist. We can't make any predictions. Let's go back here. Let's actually deploy that model. Again, one line of code. And now I'm making predictions using a random forest model.
Yep, and one thing to kind of stress here, again, it's not just the model that's being deployed, it's all of the transformers along with it. The ones that we showed, I think, are very simple, common ones, like the standard scalars. So when you're, like square feet, for example, like the model doesn't know what square feet is. It's first has to go through a standard scalar, which we scaled, I believe, just using standard deviation, right? So it's doing that for you. And as an engineer, you don't have to rewrite the code in another language in a production deemed environment to do standard scaling, for example, as well as any of the other Spark transformers that exist. They are provided for you, as well as what we'll talk about, the serialization format, as well as a deployment for all of those transformers. And so before we dive into kind of how, technical details of MLeap, just want to talk a little bit about the motivation for these projects. And the biggest one is that getting these models out into production is still too difficult for a lot of organizations. Both Hollin and I have been on teams where model deployments and pipeline deployments have taken weeks, months. We've actually been a project where it took over a year. And that's because there's just like a little bit of a knowledge gap between data scientists and engineers that everybody, I think, is very familiar with, where engineers, they do their research, they use, they build models, but then engineers often have to recode all of that in a production environment, and that's what we're trying to solve. And we believe both of those groups want to do better. We believe that the winning technology in the machine learning space will be the one that enables both data scientists and engineers to collaborate on a single platform. And we believe Spark is that platform for a couple of reasons. Because if you think about it, when Hadoop came out, it gave us HDFS. So essentially, that solved the problem of having your data in disparate data sources, like in weird SQL servers that data scientists had to pull together, and then engineers also had to replicate the same data pipelines or ETL pipelines. HDFS just took care of that, right? Because everybody's using a common data source. Then Spark came along and essentially gave a common language to both researchers and engineers through ML libraries, machine learning APIs, right? At least now we're talking the same language. And what we are providing with MLeap and Combust is an extension to that, and really trying to eliminate any recoding that has to get done to be able to deploy your model out, like as Hollin mentioned, to either the cloud or even edge devices, essentially providing that functionality. And one thing I kind of like to address are like the existing technologies in the space, because they exist, they're powerful, a lot of companies use them. The goal of MLeap is not to compete with any of them. Really, what we're trying to solve for is give the engineers the time back that they would have otherwise spent on recoding the researchers' data pipelines, transformers, and getting these models out into production. We really are trying to solve for, eliminate that step of recoding models and give you the ability to deploy models literally in seconds, like we just showed you. And we're doing it in an open sourced way as well. And now let's dive in a little bit into the technical details of MLeap. But just to establish a few terms that we've used throughout this presentation, I'm not sure if everybody is already using transformers and pipelines. But a transformer, there are two types. I think essentially, you can think of it as a function, right? You're trying to compute a new feature or a new variable, right? Where you have a vector of inputs and you have a vector of outputs. It could be a one-dimensional or n-dimensional vector of outputs. Essentially, it's your functions to create new features. But transformers are also models. So like a linear regression, a random forest is a transformer as well. And a pipeline is just a way for you to sequence those transformers together. And when you execute a pipeline, you're essentially taking step-by-step operations and generating your features that you need for the model, as well as training your model. So sort of the components to MLeap. We'll talk about Combust ML later, but we'll start off by talking about some of these components to MLeap. There's MLeap Core, which has your feature builders, all of your machine learning models, all that kind of stuff. The runtime, which gives you your data frame, like data structures, your transformers, all that. We have Spark integrations, so that you can, obviously you saw us just serialize a pipeline to bundle ML so that we could deploy it. And then finally, we have the bundle ML library itself, which is our serialization format.
And all of this is open source. And actually, right now, we're also working on scikit-learn integration. So if you build a pipeline in scikit-learn, you should be able to export it to the same exact format and upload it to our servers in pretty much a very similar way to what we just showed you.
One thing to mention, when we started first talking about MLeap, especially the core components and the models available, we only had like a few of them really as proof of concepts. Today, MLeap supports the majority of feature transformers. I think we support like 95% of them. I think the only one we don't have is like the SQL transformer. But everything from simple ones that we showed, like standard scalar, to more complicated ones like principal component analysis, you can today serialize and deploy to production, like again with the .deploy method that we showed you earlier, without the need to recode it in a different environment. We also support all of the regressions, a majority of classifiers, a few clustering algorithms, wrapping up neural networks right now. And then one thing that we are providing also is the ability for you to write your own custom transformers, so that you're not limited to just a set that, that Spark or Scikit or any other technologies may have.
Yeah, and so these core components are really just the algorithms themselves, and then MLeap Runtime is really what brings everything together. So in MLeap Runtime, you're going to see this thing called a leap frame, which is essentially just a lightweight Spark data frame. It supports, doesn't quite support as many data types as Spark data frames do, but it supports a lot of them. It supports custom types, so if you want to put a WAV file or a case class or a JPEG or something like that into your data frame, you can do that, and then you can write a custom transformer for it. So if you want to write a custom transformer for a JPEG file that outputs a set of features, you can do that quite easily with MLeap Runtime. And in fact, it only takes a few classes to then implement the serialization for it so that you can deploy it to our servers. And then you deploy it to our servers along with your jar file that has the transformers in it, and magically you can start serving your models from the same exact model servers that we were just showing you.
Yeah, and I think one thing to quickly mention there is there's no dependency on Spark context, so that actually enables a lot of the fast execution, because your data, when you're scoring, doesn't have to be distributed. So that's where a lot of the performance gains come from.
Yep. Yeah, so no dependencies on Spark at all. No libraries, no Spark context. One of the things that's a little bit different about how MLeap works than Spark, they're actually very similar in a lot of ways, in terms of the transformer pipelines at least. But MLeap doesn't actually directly transform your data frames. It goes through this thing called a transform builder. And the cool thing about sort of abstracting the actual transformation away from the data frame is that you can do a couple cool things with it. One, you can do what you would expect. You can transform a data frame with it. So you can take what we call a leap frame, which is just this lightweight data frame, and you can actually send it through your transformer pipeline, and you can get out the predicted results that you want. Some of the cooler things that you can do with transform builders are we actually wrote one that lets you execute your MLeap pipelines on Spark data frames. So we're taking all of these user-defined functions that you've built out in your transformers and in our standard library of transformers. We're converting them to Spark UDFs, and then we're executing them against the Spark data frame. And we support, again, we support conversion between custom types in Leap frames as well as user-defined types in Spark. So that all happens seamlessly. As long as you have a UDT in Spark and you also have a user-defined data type in MLeap, they'll convert between each other just fine. One of the last things that we're just starting to look into is actually compiling your transformer pipelines into either highly optimized JVM code or even a C library, because one of our big goals is to let you take these pipelines outside of the JVM, deploy them to iOS, deploy them to Android, deploy them to edge devices, wherever you want to. This is just a diagram of that example pipeline that we showed you. So fairly straightforward. You take your continuous features, you scale them, you take your categorical features, send them through a string indexer, send them through one hot encoder, take all those outputs, combine them into a final feature vector, and then send them through a regression pipeline. And this is just the proof of concept pipeline that we used for MLeap, and it's actually proven to be a quite useful tool in just creating easy one-off pipelines to sort of demonstrate to everyone. Bundle ML. This is our serialization format that we've developed. It's entirely based on JSON and protobufs. And the reason for that being is that JSON and protobufs are supported on pretty much any environment, any programming language that you can think of. So one of the big goals of MLeap, one of the big goals of BundleML, one of the big goals of Combust itself is to be a highly portable platform. So you can deploy these things anywhere that you want to, all on a common runtime. So normally we serialize these things to directories, but you can actually take those directories, zip them up, and then if Mikhail develops some new version of a model, he can literally just send me a zip file. I can take that zip file, I can deploy it to Combust, I can deploy it to a local service, I can deploy it to my custom API that I built myself. I can deliver it to a client if I need to, if I'm a data science company and I want to build models for people. This is a way that you could deliver models to your customers. So it's just very easy to send these things around.
Yep, and I'm actually going to let's show what the actual bundles look like.
Oh, yeah. Here, let's show you what these things actually look like. So I actually serialized that random forest model that we just built. And this is the structure. There's a bundle JSON, which just has some basic information about your pipeline. You can actually serialize in mixed JSON and protobuf mode, or you can serialize just as JSON, or you can serialize just as protobuf. So this is saying we're using mixed mode. We have a feature pipeline. We have a random forest regression. That feature pipeline is, here's the continuous feature assembler, which is just taking a whole ton of features and building a vector out of them. We have a scaler, which is taking our unscaled continuous features and outputting scaled continuous features. And so you'll see that there are two files for each of these transformers that you have defined. There's this node.json, which defines sort of the input and output shape of your transformer. And you have this model, which is actually defining all of the data that your model needs in order to execute. So in this case, we're talking about a standard scalar, and it's scaling based off of standard deviation. So we're storing a vector of all of the standard deviations of all of those features in the unscaled feature vector. Just real quick look, this is what a string indexer looks like. Again, the node defines the shape. And if we look at your random forest model, we have the node here. We have your model with your tree weights, a list of your trees, the number of features, just stuff that it needs to execute. And then this is a fairly unreadable file, but this is actually storing all of your decision nodes. And again, just some metadata about a decision tree. The last module that I want to talk about is MLeap Spark. And this is a fairly straightforward module. It used to be a lot more complicated. This provides a few functionalities, the first one being that you can take those Spark pipelines that you have and you can serialize directly to BundleML. We've had to build out a few extensions to Spark itself, and this is just so that we can extend the functionality because we needed to get probabilities out of a one-verse rest model, for instance. So we implemented our own version of one-verse rest that's pretty much exactly like the Spark code. It just lets you output the probability as well. One hot encoder we had to re-implement because of the way that it's implemented in Spark. So if you want to use one hot encoding, you have to use our version right now, even though we are building out a way so you won't have to do that in the future. And then just sort of extending general ML functionality with MLlib functionality. So we implemented support vector machine that's based off of the MLlib implementation. The last thing that MLeap Spark lets you do is, I was talking before about those transform builders. Well, we implemented the Spark transform builder so you can actually take your MLeap pipelines and you can execute them against Spark data frames. And this is really useful if you're trying to share features between researchers and your actual production pipeline. Because now you can implement a feature as an MLeap transformer, and you can have it execute exactly the same on our API servers as it does when you're actually building your research data set. Combust ML Cloud, this is those API servers that we were showing you. And actually, this is a little bit more than what we were showing you. This is a cloud of model servers that's going to be automatically scaling for you on Mesos, on AWS. We want to open source a lot of the model server code that we're writing. We just need to clean it up a bit and add some stuff to it, document it before we do release it. Like we showed you before, it's literally just one line, .deploy your Spark transformer pipeline, and then you have a running model in our API servers. So yeah, they're very efficient. Even right now, with very few optimizations, we're still getting average 14 millisecond response times for that linear regression pipeline that we showed you. And a lot of that, most of that, is actually spent not in executing the pipeline itself, but actually in serializing and deserializing all of the JSON for it. Here's a graphic representation. We just did some Apache benchmarks against our model server. Again, uncompiled models, we're not doing a whole lot of optimization on model execution itself. We're not doing a whole lot of optimization on JSON serialization on our serialization format. So there's a lot of improvements to be made. But these are still extremely fast response times. We're talking an average of 14 milliseconds for the linear regression, an average of 24 milliseconds for the random forest regression. 98th percentile for the linear regression, I think, was something like 24 milliseconds. And the 98th percentile for the random forest models was something like 40 milliseconds. So very fast still.
Yep. One of the reasons why we decided to open source a lot of the model servers is like, so last few times we presented, it was like, okay, great, we have MLeap, it can serialize your Spark pipelines and give you a way to deploy them. But I think the big question was like, deploy them to what? And a lot of folks, we essentially like had to show them how to stand up their own API servers. And that's a learning process in its own. So what we're doing is we're actually gonna, for anybody that does want to try it, if you go on to Combust.ml, you'll be able to sign up where we're actually gonna send you a link to a public hosting service. So when you train your pipeline of transformers as well as the models, you want to try out .deploy for yourself. We'll give you a common space where you can go ahead and deploy your model literally like we did today and have a model server running in seconds. The only caveat there, like we won't be supporting custom transformers, it's just the ones that are available in Spark and MLeap. For private hosting solutions, we actually just did a deployment for a company that's deploying these models not only to the cloud, but to actual edge devices. So that's actually kind of neat. Like today, you're able to train your models on Spark, collect all of your IoT data, process it with transformers, train models, and be able to deploy them to essentially like Raspberry Pis or edge devices. So for that, obviously, public cloud is not the solution, but if you are looking for some sort of a more custom deployment, reach out to us. We're happy to work with you and help you deploy this on either like Mesos or AWS, help you with custom transformers, and then also kind of what we talked about, compiling to bytecode. And then the third thing that we're kind of starting to work on is like data science, before I think it used to be a lot for folks that had a research background, a stats background, engineering background, but things like Spark has really democratized data science. So a lot of non-technical folks are actually able to plug in and kind of like understand the math that goes on behind it and be able to spin out models. So one thing we're also providing is like connectors to like databases like Salesforce or like other CRM solutions, as well as like inventory management systems. So if you're not a technical user and you want to be able to spin up a model with a clever UI and some guidance to make sure you don't make some basic data processing or machine learning mistakes, you'll be able to spin up a model literally within minutes and be able to deploy it as a proof of concept for your organization as well. And then also, we mentioned this before, kind of like future of MLeap. We talked about like integrations with like scikit-learn. And the belief there is like, okay, a transformer in scikit does the same math as a transformer in Spark, right? Like a standard scalar in scikit is doing the same thing as a transformer in Spark. So we having something like bundle ML as a common serialization format is very powerful because we can now serialize other technologies to that and also provide the extension of .deploy. Also being able to unify with Spark core libraries. So there's the MLeap local project. As Spark builds that out, more models become or go into MLeap local. We'll essentially remove a lot of the duplicate code that we have to maintain between MLeap and Spark. And then, of course, on interface for PySpark, because right now all of it is Scala. And then, yeah, that's it. Thank you very much, everybody. If you have any questions, feel free to, ask here, and feel free to reach out to us. Also, we'd be happy to show you how to use MLeap for your projects.
Thanks, everyone.
All right, so just to remind everybody, we have microphones there and there for questions. And remember, if you're asking a question, please get very close to the mic.
Hey, I have a question. What's the solution for keeping models updated after they've been deployed to the model server, especially if you want them updated in an online manner based on newer data?
So it's literally just calling that .deploy method. You can actually redeploy any model to the same endpoint that you want to. So when you call .deploy, you're specifying the name of the model that you're deploying. So if you train a linear regression and you find that, hey, actually random forest performs better, then you train your random forest model in Spark, call .deploy, deploy it to the same space that your linear regression was deployed to, and now it's serving the random forest model.
But if you wanted the models updated in an online manner based on newer data that you're performing the predictions on.
Sure. So, if you have Spark Online Learning set up or something like that, then periodically you can just call .deploy with the new model. So say every minute or however fast you want to update it, just call .deploy whenever you have a new model.
OK, thank you.
Yep.
Cool.
Do we have anybody else?
Yeah. In reference to his question, is there any downtime associated with redeploying a model?
No, it's completely atomic. So you won't start serving results from your new model until it's replaced the old model. So while you're deploying, there's some time it takes to upload it. There's some time it takes to unzip it and then load it into memory. But it'll just be serving your old model during that time.
All right, let's give our speakers one more round of applause.